All right, let's talk about vapor pressure of solutions. And Rout, we have something called Rout's law, which tells us how the vapor pressure of solutions differ from vapor pressure of pure liquid. So this is the vapor pressure of the pure liquid. And so this is a mole fraction. And so the basic point of this is when you have a solution, the vapor pressure decreases. And so we got graphs and this kind of stuff. This is showing a process that we can take advantage of this with, and that is distillation. Distillation, if you, let's say you put ethanol in water, ethanol has a higher vapor pressure than water. So what will happen, ethanol has a higher vapor pressure but lower boiling point. And so what we can do is we can boil off the ethanol. The water would stay down here. Ethanol vapor would rise up through here, and then when it hits this is water cooled. And so the ethanol would condense back into liquid, and we should get pure ethanol over here. And so we could use distillation to purify liquid mixtures. We can use Rout's law to figure these things out, but it turns out Rout's law is for ideal solutions. If the solutions start to deviate from ideal behavior, then we don't get very nice distillations. And so this is propanol. What happens with propanol is if you try to distill it, you end up here at the bottom. This is called an azeotropic mixture. You don't have to know that, but basically the purest propanol you're going to get is around 70, less than 75% propanol, 25% water. If you try to distill alcohol, like grain alcohol, you know what the purest you can get from distillation is? 95% ethanol, 5% water. That's the purest you can get because of this deviation from ideal behavior. That's well. This is distillation. Another thing that you see is osmotic pressure from vapor pressure lowering. There are different ways of thinking about osmotic pressure. If these two solutions have different vapor pressures, then we're going to get a net transfer of water from one solution to another. And we can see this here on the board. I tried to illustrate something here. And so over here on the left, if we just have pure water has a vapor pressure that's like this. But if we start putting some solute in there, like sodium chloride, then the sodium chloride solution is going to have a lower vapor pressure because now we have the solute. We're going to get less vaporization off the surface here. It's a lower vapor pressure. And so on this side, you have this pressure, pushing down on all surfaces. And it's pushing down here, vapor pressure. On this side, you have this pressure pushing down, but on this side, the pressure is less. Now, separating the water from the solution here is a semi-permeable membrane. A semi-permeable membrane allows water molecules to pass back and forth, but does not allow the salt to pass back and forth, the sodium chloride ions. And so the end result is this. You got more pressure on the left. If you got more pressure on the left, it's going to push down the surface on the left and push up the surface on the right. And so as the surface rises up on the right, because the water is going to be transferred or pushed through the semi-permeable membrane, this will balance out when the vapor pressure plus the liquid pressure matches the vapor pressure over here, so the two pressures are equal. That's it turns out the liquid pressure here is called the osmotic pressure. That's the amount of pressure we have to apply to keep the two levels the same. In addition. And so, looking at this illustration here, this is another way of thinking about osmosis. Osmosis is here. Not only are we going to have fewer water molecules vaporize off the surface here because of the solute, we're going to have fewer water molecules move from top to bottom than from bottom to top. As you can see, we just have fewer water molecules there. Concentration's less. And so here we're going to get net migration of water up. Can you see that? Because the two rates are different. That's called osmosis. Osmotic pressure is the pressure required to stop that net migration of water. net migration of water to the more concentrated solution. We can calculate the osmotic pressure based on molarity here. The higher the molarity, the greater the osmotic pressure. The more solute we have in there, the less vaporization we're going to have off the surface. And so here we can see another illustration of osmosis. And the natural tendency here is for the water to go from pure into the salt, because what we want to do is we want to equalize the two concentrations. Because when we equalize the two concentrations, then they'll both have the same vapor pressure. But we can prevent this from happening by applying an external pressure. The external pressure would be the osmotic pressure. So osmotic pressure would stop the migration. But what happens if we add more weight, more pressure here? If we have more pressure here, what we can do is we can actually reverse the spontaneous process. That is, if we keep adding more and more pressure, more and more weight, it pushes down the right side, forces water this way, and so the salt water actually becomes more concentrated, and we end up with pure water on the left. This is called reverse osmosis, and so this person is pumping in seawater here through the membrane to get pure water out. Osmotic pressure depends on vapor pressure. Vapor pressure depends on how concentrated the salt solution is. And so when we're thinking about salt solutions, we can think in terms of hypertonic. Hypertonic means more concentrated. Isotonic means the same, and hypotonic means less concentrated. That's going to be relative to, this is a blood cell. And so if you put a blood cell in a hypertonic, the water inside the cell wants to migrate out because the solution out here is very concentrated, like brine, salty. And so what happens to the cell is it shrivels up, becomes dehydrated. In isotonic, the water migrating in and the water migrating out are equal. In hypotonic, we get not migration in, and so the blood cell balloons out, grows bigger, causing potentially cell rupture. Yeah, that's osmotic pressure. Osmotic pressure is a colligative property. Colligative just means a collection of properties that depend on the same thing. We have two more colligative properties. We have freezing point depression and boiling point elevation. So far we talked about vapor pressure, lowering, osmotic pressure. Now we have these two. These two we can most easily see on the phase diagram. If the this is the vapor pressure curve here of the liquid in the phase diagram. If the vapor pressure is lowered, then what happens is the boiling point changes. The original boiling point was here, but if the vapor pressure is lowered, then we need more temperature to get the vapor pressure to equal atmospheric pressure. And so the normal boiling point changed from here to here. And also the freezing point, or the melting point, changed too. The original melting point were here. Now if this lowers, this melting line is going to lower as well. And so the new melting point's down here. And so we call this boiling point elevation, freezing point depression. We can calculate it. We're going to skip the calculations. Some applications, spraying solutions to de-ice jets, pouring salt on roads to de-ice roads, etc. So those are some colligative properties. You just want to have heard of them, but not much else. And this you want to have heard about, Arrhenius in 13.9. Deals with deviations from ideal behavior. If you have sodium chloride, ideally it splits up into two ions, a sodium ion and a chloride ion. The two ions are independent. But it turns out at higher concentrations, when there are a lot of sodium ions and a lot of chloride ions, they don't stay independent. They start to pair up. And so when you get to about 1 mole out of sodium chloride, about 10% of the ions are paired up. That is, they're still hanging around each other. They haven't completely separated. This deviation from ideal behavior is more severe for higher charged ions, which is to be expected because higher charged ions are going to have stronger electrical attraction. And so here for magnesium sulfate, it's more like 50% paired up. The magnesiums and the sulfates just don't split apart. You know, the crystal's gone, but the magnesium ions and the sulfate ions are hanging around each other. And you can see that for these as well. And so this is deviations. And so we can correct for those deviations. You know, when the ion concentrations get high, you see you get these clusters and they don't behave independently or as independently as before. We can correct for these, but we aren't in Chem 1A or Chem 1B. And so this is deviations from ideal behavior caused by interionic attractions. And so these solutions don't behave ideally anymore. The final section of chapter 13 shows the difference between a solution and a colloidal mixture. The only difference between a solution and a colloidal mixture is this. The solute particles in a colloid are big enough to scatter light, whereas the solute particles here are invisible to light. I mean, they have some color, you know, the rust color, but they don't scatter like this. When the solute particles get too big, then we have what's called a suspension, like this. Here the solute particles are too big. Eventually these solute particles are going to fall to the bottom of the container. But here the solute particles are so small they stay permanently suspended. And so this is a rust colloid. Have you dealt with colloidal precipitates before? Yes. Right. How do you get rid of colloidal precipitates? Heat it up. Heat it to get it to coagulate so that the particles grow and precipitate. There's other ways too. Rather than heating, they're adding aluminum sulfate to help neutralize the surface charges to get them to precipitate. Here's dialysis. Some applications. That's it. All right, so what we're going to do next is we're going to check out the model kit, and then we're going to build 3 models, and we'll talk about those models, and then we're going to see a video, and then we'll check out.